condition with sum over I next to j, sigma I scalar product with sigma j. And this definition easily extends to spins that live in S1, S2, S3, and so on. So the BKT transition, as we will see, it has to do with the S1 valued spin system. And S1 here is sigma I, is e to the I theta I, which lives in the unit circle S1. So, at the end of the last lecture, we reached this, this slide, which suggested that despite the theorem by Mermin-Wagner, about which I gave a sketch of proof, different steps of the proof, we've seen that the XY model, and in fact the S2 valued model, and all of these, they never have any long-range order, any symmetry breaking in dimension d is equal to 2. I briefly mentioned why in dimension d equals to 3 and higher there is a different phenomenon, maybe closer to what one would have in Ising model. But in dimension 2, it seems the system is trivial, there is nothing going on. And in the early 70s, Berezinskii-Kosterlitz and Thouless, despite this theorem, they found out that there is a nice phase transition which separates a phase, a high temperature phase with exponential decay of the correlations, and separates a low temperature phase which has power law decay of correlation. And this is called the transition point, is the BKT point. The transition is supposed to be of infinite order, so this is rather unusual. The Ising model is a second order phase transition. The free energy, the second derivative blows up at Tc, but it has a derivative, first derivative at Tc. This one has as many derivatives as you wish, but it's not analytic at that point. So the goal today will be to to understand a little bit from the math side what is going on, why there is such a phase transition, and how one can prove such a thing. I will first start by telling you how physicists came up with this phase transition. It will involve vortices. In fact, there is a nice mathematical way to understand those vortices, but I will be a little bit brief about those. If you have questions, I'd be happy to answer later. So this was a recap of all the models.
It's okay.
I have the same issue as Philemon 2 days ago. Let me play with the wire. I don't have many slides to show you, so. Why it works. There is not much here. We have the Ising, the XY, the Heisenberg.
Change this way.
Ah, okay. I can remove the glass. Thank you. Okay, so, and as I mentioned last time, this nice phase transition which involves vortices is conjectured not to exist when you reach systems whose continuous symmetry is no longer abelian. So this, if I have time, I will try to say some words at the end why this is conjectured to be the case and how one may try to start analyzing those systems. This is, I really like this conjecture here, which goes back to Polyakov. But most of today we will focus in this d equals 2 and S1 valued spin system where there is this algebraic decay versus exponential. The discovery of this is Berezinskii-Kosterlitz-Thouless, early 70s. The first proof of this theorem is a very famous paper by Thouless and Spencer, which goes back to 1981. I will tell you some words on what's going on here. And then in 2021, there were two very nice works by Van Engelen-Borglis and the other one by Eisenman, Harel, Peled, and Shapiro, which provided a new proof of the existence of this phase transition. Both of these works are based on a new proof of delocalization of a dual model on which I will insist a lot about, which is called the integer-valued Gaussian free field. So it's the same Gaussian free field as usual, but with the further subtlety that it's conditioned to be to have its values in the integers. And this little condition, this strong conditioning, is very nice because it breaks the Gaussian behavior and it induces a phase transition on these systems. So all of these proofs, at some point, they go to the dual model on which I will spend some time about. But before going to the dual, I want to tell you how physicists understood that phase transition was at stake in this system. So one way to explain this is to go back to the way the Gibbs measure looks like. So each config, so this is not great here. I have a sigma, I have a theta, but sigma is this e to the I theta. Each configuration of S1 valued spins has a weight, a Radon-Nikodym derivative, which is proportional to this Gibbs weight that we have played with last time. And the first thing that we can do is that we can Taylor expand this cosine as I did last time. So this means that I don't switch off the slide yet. But if I take this Gibbs weight, this is more or less exponential beta times the number of edges minus beta over 2 sum over I next to j theta I minus theta j squared. So of course this is completely wrong because by thermal fluctuations there will be edges where the gradient of angles will be far from 0 or might be very close to 2 pi, for example. This is far from accurate, but let me assume this for a while. So when we play with Gibbs measure, constant terms, they don't play any role. If you're more on the physics side, it means there is an energy profile. If you shift an energy profile by the same constant for everyone, it doesn't change the physics. So this is still exponential minus beta over 2 times sum over the edges in my graph theta I minus theta j squared. And if we look at this, it looks like the XY model might look a little bit like a GFF. So if we are courageous enough, we may say that once we look at this Gibbs weight in this fashion and we remove all the quartic terms, all the 6th order terms and all that, maybe e to the I theta I, or e to the I theta x, x in Z2, maybe this will look a little bit, so we can try a guess. Maybe this will look a little bit like e to the I times phi of x, where now phi is a Gaussian free field indexed by the points on my Z2 grid. And if you don't like the Z2 grid because the GFF is not defined pointwise but only up to a global constant, you can take a huge n by n box and then it's well defined. And if you believe in this guess, then you're in good shape because you will notice that the 2-point function between two distant points x and y, this will be the same by symmetry as e to the I theta x minus theta y. And by this guess, this may be close to expectation now under the GFF measure. of e to the phi x minus phi y. And this is now a Gaussian computation, so it's much easier to compute what this is. And when you manipulate the Gaussian free field, expectation of e to the I of a Gaussian we know how to do. This will be e to the minus 1/2 variance of phi x minus phi y. And the Gaussian free field, the variance of the Gaussian free field at x minus the Gaussian free field at y. This involves random walk in Z2. This will be logarithmic in the distance between x and y. So what we end up with here is minus 1/2 log x minus y, or roughly this at large distance. And there is something I dropped along the whole discussion, which is there is a dependence in beta. So maybe there is a function of beta here, which I should have kept track of this through all the computation, but I did not, because this dependence in beta is subtle, and I will go back to it. But if we believe in a close enough relationship with GFF, we end up with a 2-point function which is exponential of a constant which depends on beta times the log. And itself, this is what we hope to find, which is 1 divided by the Euclidean distance between x and y to a power constant, a critical exponent which depends on beta. So what physicists did is more than that, because this I just Taylor expanded, made some assumption. I claimed it was Gaussian, and we get this result. It's more than that, because first, I didn't explain what this would be. And second, this explanation may predict that you always have power law decay, whatever beta is. And this is very easy to show that it's not the case when the temperature of the XY model is large. So, at the very least, if this intuition might be correct, this would only hold when the temperature is low enough. So I will go back to the slides. For a short while.
But if you pretend it's Gaussian, then this is explicit. You can very easily find it.
Sorry?
I mean, you can very easily find this exponent. I mean, it's like 1 over beta or something. If you pretend it's Gaussian.
But that's true. So if I pretend the Gaussian, I can replace this 0 2 pi variable by the r variable without affecting this, then indeed I can predict exactly what is this f of beta. I think we can predict up to 2 pi that I never know where this is with the green function. But yes, you can do the whole computation, and maybe this would be something like 1 over 2 pi times 1 over beta. But it turns out that in this approximation there will be a correction to this 1 over beta, which will pop up. So what physicists did is that they started in the same way that we did here. So they did a Taylor expansion, and then they noticed that what is very important is not quite the value of the angle at I, but rather the gradient, how much angle you accumulate when you go from I to J. So what is the gradient field of angles? And this can be written like that, and the right tool to try to analyze this is to view those gradient of angles as the random one form in the plane, which tells you if I move along this path and the temperature is very low, maybe I can understand by how much the angle is following along this path, which is what one forms are made for. So if temperature is very low, if you are close to a ground state and you follow along one path, maybe you can tune how do you move along the S1 circle. But if you do that and you take another path, as usual with one forms, it might be the case that if you go from this point to this point with this gamma 1 path, but then you choose to go from this point to this point with some gamma 2 path, and you manage to follow step by step where the angle is going, you will want to arrive at the same angle, but there could be a difference by 2 pi, 4 pi, or minus 2 pi. So in other words, this one form may not be an exact one form. There may be defects, And that's what vortices are measuring. So vortices are saying that there are some plaquettes where when you go around the plaquette, you accumulate a monodromy of 2 pi, 4 pi, minus 2 pi, minus 4 pi, and so on. So what they say is that when you do this Taylor expansion, there are, in some sense, two issues. One is that you have quartic, quintic, 6, and so on, all the terms in the RG flow that Antti knows very well. So you may want to follow those. But maybe an even more serious issue is that this field is 0 to pi, not R-valued. And there are monodromies of the associated one forms that you have to investigate. And those come with vortices that you can affect or not to the plaquettes of Z2. So what they say is that the Gibbs measure of these one forms, when you analyze what a one form is, it arises from two possible randomness. So it's called maybe Hodge decomposition. One part of this not necessarily exact one form comes from zero form. So you have true function that you differentiate. You take the gradient of true functions. And another part comes from two forms via the D star or the coderivative. And those would look like that. So these are typically things, the gradient of this doesn't come from so the theta angle will not come from a zero form because you will accumulate a 2 pi monodromy when you go around the curve. So their analysis says that the fluctuation of this one form field is made of two fluctuations, and they justified for another model that I will introduce that these two sources of fluctuations are even independent of each other, which is very deep. So one is the zero form, and this one is exactly the GFF. And the other one is called the Coulomb gas and comes from fluctuations of those vortices. And this one is much less linear, and this is the one which is responsible of BKT. So what they understood is that the two-point function has two contributions, one which is exactly what I have sketched here. So there is this 1 over beta times maybe 1 over 2 pi, exactly this, whatever beta is, so this is always polynomially decaying. And another one comes from those Coulomb gases, those vortices, and those, depending on the temperature, will be either exponentially decaying or polynomially decaying. So the BKT transition is really on this Coulomb gas of defects here.
So if you just try and like pick out the exact bit by testing against the correct set of test functions, is it easy then to show convergence of this thing to GFF?
So there is a slightly easier model than this one that I will introduce, which is called the Villain model. And in this Villain model, you can single out what is the zero form part and what is the vortices part. And this zero form part, you can easily prove that it's GFF. And then you can test it against macroscopic functions. So yes, so for the XY model, it's a little bit less clear, but for the Villain, it's grand.
Well, in principle, you could test your whole d theta. You could just test it against things like divergence, and then you would just see the zero form part.
Right, that's true. Another issue here is that my d theta for the xy, this is a modulo 2 pi defined, so I don't want to say something wrong. The Villain, one advantage of the Villain is that you can do a cable extension a bit like Titus Lupu did a lot for GFF, and this removes all possible ambiguities with the modulo 2 pi. So physicists understood the importance of those vortices, of those places where there is a local monodromy, but they did something more. They did what's called the entropy energy argument to explain why there are few of those at low temperature and why they start having many of those at high temperature. The high temperature phase is called the plasma phase in this case of vortices. So how does the energy entropy argument work? So the idea is as follows. So I took one of those pictures by Demidov and I tried to put an indication where we would see those vortices. So there are some black vortices which go in one direction and white vortices go in the other direction, but you need good eyes and it's not impossible. I made a mistake somewhere. But maybe here we go from in the trigonometric order from green to red to blue. And the black ones, they go from green to blue to red. So at least those 2 points are correct. And the idea of the BKT transition is that when you have a vortex in one direction, it will want to be next to a vortex in the other direction. So vortex and anti-vortices, the plus vortex and the minus vortex, they like each other, a bit like electrons and protons like each other. And why do they want to be next to each other? If there is nothing next to this, let's say, plus vortex, one can ask ourselves what is the Dirichlet energy which is needed to have just one vortex at the center of this box. And the computation to compute the minimal Dirichlet energy for such a picture is very similar to the one I did 2 days ago when we did the Mermin-Wagner theorem. So I will do it now in a very sketchy way, but we will see that the scaling is very different from the spin wave, the picture by Velenik that I had shown 2 days ago. If I now want to have a vortex, we will see that this will cost a lot of energy. So energy of a vortex So if I have 0 here, so it would be a plaquette. And if I want to have a vortex here, I need to have a configuration of angles which will go around this plaquette. And I want this vortex to be alone in a huge area, so maybe in a square of size n. So there could be local fluctuations like that, but let me try to minimize the Dirichlet energy, so to take some kind of harmonic extension. There is a way to formalize this. And let's try to compute what is the Dirichlet energy of this field of angles. So when I am at distance k, between 1 and n, what is the Dirichlet energy that I will have in this circle of radius k, up to constant? Along each of these edges, maybe I should take squares on Z2, but along each of these squares, the angle is something like 2 pi divided by k at distance k. Because I want to go very smoothly, I want to produce a vortex in the least energetic possible way. So the gradient of angle here is of order this. K is the radius where I am here.
And what was that meant to be with respect to n?
And k is any radius between 1 and n.
Okay.
And then I will sum over k to try to understand the Dirichlet energy in an area of diameter n around a single vortex. So the Dirichlet energy of this theta field with a vortex at 0. So I recall that this is defined as the sum of I next to j of gradient of theta squared. And this will be larger or equal the sum from k equals 1 to n. So I am summing over all those layers between the vortex in the middle all the way to the size n. The Dirichlet energy accumulated along those circles. And since circles, they are not very good for lattice, maybe you want to sum over squares, but this will give the same up to constant result. And now I have up to constant k edges along this circle, and each of those is costing 2 pi over k squared, Dirichlet energy. So altogether, this is of order sum from k equals 1 to n, 1 over k, which is log n. So this is the same log n as we had with Mermin-Wagner, except in Mermin-Wagner it was a 1 over log n. So this very slow spin wave, which didn't create a monodromy, this was a very low energetic wave. This one, which needs to produce this defect at all scales, requires a lot of energy. It requires log n. And now we are in good shape for the crush of the paper by Berezinskii and by Kosterlitz-Thouless. Their analysis is to ask the following: if beta is large, if the temperature is low, how does the gas of vortices look? And they claim the following. They claim that each time you put a plus vortex, you want to pair it with a minus. And they asked how many pairs of vortex-antivortex can you put in an n by n box that are macroscopic, that are far from each other. So the question they asked is how many macroscopic pairs of vortex anti-vortex can we expect in an n by n box. So in other words, how many things that are distanced from each other, say a distance more than 1/2 times n, can one hope to find in such a large n by n box? And here they made a computation which is very approximative, but which says something. So they made a kind of first moment argument. They said, let's count. So the number, the expected number of such pairs by a counting argument should be the number of those. So how many such pairs do I have? I have n squared choice for the plus, n squared choice for the minuses. So I have n to the 4 such macroscopic pairs of points. And now, what should be the probability that this chosen pair of vortex exists in the system? They claim that this will be proportional to the energy cost that it requires to exist. That's where the argument is somewhat fishy, because now they pretend that as if you had no other vortices in the system because beta is large, they pretend that this all the way to n over 4 is going to locally look like what I've drawn, with some small thermal fluctuation. And this is the vortex which will be in the other direction. So each of these two vortex cost log n over 4 energy. So then they claim that this is maybe twice log n over 4, but there is a beta here. It's the beta of the Gibbs measure. So the argument is that if you look at this first moment, which is not fully rigorous, far from being fully rigorous, there is a competition between the entropy and the energy, and e to the minus beta log n, let me forget about the n over 4, this is very loudly speaking, e to the 1 over n to a constant times beta. And so they were more careful than I was with the constant. And so they claim that if beta is large enough, this goes to 0, and those macroscopic vortices no longer exist. So thanks to this entropy energy rather small argument, they predicted that at low temperature, the system looks like that. So at low temperature, at beta very large, they predicted that the Coulomb gas is very far from being Poissonian, that they are by thermal fluctuation, you cannot prevent the existence of vortices. You will have a positive density of vortices, but each time you will find one, with high probability there will be another one next to it. And they have a notion of what is the intensity, what's the probability to see a plus somewhere in the system. It's something like exponential minus constants beta, but it doesn't degenerate with n. But they had the intuition that vortices come in two pairs, and very rarely there is maybe a vortices which is at distance a power of n, which depends on beta. But they don't manage to go very far. And this phenomenon, they called it vortex binding. So this is vortex binding. So binding means that they are so much attracted to each other that they form those pairs. While at high temperature, at small beta, they predicted that the system becomes a very high temperature. So high temperature, low beta. Instead, the entropy should win. Now beta is very, very small. This is not so much of an issue. So now plus and minuses, they are not quite independent from each other, but they don't care so much about the other phases. And the name is very good, it's called the plasma. And I don't know much plasma, but the plasma is you heat up the system so much that electrons go out of the ions, I don't know how it's pronounced. It's a whole soup, they move fast, they don't care so much about each other. And that's what they predicted for this gas of defects in the high temperature. So the BKT, we can see it here. If I remove this, there is the line of temperature. Let me draw it like T. And there is this BKT point, T BKT. And the real mechanism behind the BKT transition is that at and below this point, there is supposed to be vortex binding. And above that point, you start having exponential decay of correlation. And in the terminology of Coulomb, this is called screening. Screening in the sense that to measure whether you have such a very high fluctuation system, you can try to put a particle with a 3.5 charge, which the system may not like to see, and the system is so fluctuating that it will manage to put sufficiently minus around to screen to forget about the fact you have added a particle here. So screening, so there is a notion of Debye length. There is a lot of literature on plasma physics, and the Debye length has to do with the correlation length of the high temperature XY model.
So what's special for the 3.5? Why is fractional special?
Fractional is special because in the partition function of the Coulomb gas, which I did not write down, you are summing over all possible integer values of the effect at each plaquette. And if you insert in the partition function a +5 charge, in the partition function it will be invisible. While at 3.5, you really modify the partition function, you are in z plus 0.5 in this case. And it's not clear that the ratio of the two partition function will be of order 1 or will be extremely small. So the fractional charge, you need to insert something which, or if you were to insist that you put 5 and you are not allowed to put anything on top of 5, this would also work, but this is hard to do.
I thought the screening phenomena is also for integer charges.
Yes, so I think you could.
Misunderstood what screening actually means.
I think you could phrase it for integer as well, but the proof of Relation-Spencer, it doesn't work.
Oh, they prove the sort of a fractional charge.
Yeah, so they only have a proof that at low beta, at a low temperature, if you insert a fractional charge, the ratio of partition function does decay to 0. And that means that inserting a fractional charge, the system is unhappy about it. It doesn't manage to resolve it by this binding phenomenon, and this is rigorously proved. If you force an integer charge, probably you are right, but it's not. There is no statement like that. Are there any other questions?
So vortices are coexact one-forms, is that what you are?
You might be right, but I'm not familiar.
So like they are the star of a two-form? Is like the
Yes.
diagram? Okay.
Yes. Or rather, for me, the vortices are really the plaquettes which you insert those into the D star to produce the theta field. But it's equivalent.
And like a negative vortex would be what? Like what is the difference between a positive vortex and a negative?
So if I have this will be a side remark. But if I have in the Hodge decomposition, if I have a two form, for example, I put something here. Out of this two form, which would be 0 everywhere else, I can produce a one form. So something like a D star Laplacian inverse of this one plaquette that I have here, it will produce for me a one form. And now if I put a -1, this will produce a reversed one form, and that will be an anti-vortex. So a vortex is not more important than an anti-vortex, it's just a convention, but once you fix the convention, a vortex will want to be close to an anti-vortex.
Actually, that D star of the two form is real valued, right? So why?
Oh, that's a very good point.
Yeah.
So in the villain model, so there I'm going a bit further away than I wanted, but in the villain model, there is an equality in law between the theta field. This will be equals to a GFF. So this one has to be at the right beta inverse temperature. And then it's plus something like 2 pi B star Laplacian inverse of a vortex. This is real valued, this is real valued, but the equality in law is understood modulo 2 pi. Okay, but this answer of the question is, we don't need it for the rest of the lecture. I didn't define most of these objects, so I close the parentheses. But indeed, the fact those are real valued is you need to work with this. If you are interested, I can give you a reference for this. Is a paper I wrote with Avelio a few years ago for this equality in law.
Also, did you say the two terms are independent?
And this is exactly independent of that. It's for the villain. Which I didn't define. So
But I think you said something like the two terms are probabilistically independent. That's a rigorous statement.
Yeah, so if you don't like this 2 pi, you can set the e to the I theta x field is really in law. The e to the I phi x times the e to the I this complicated function of the group. And those two complex fields are independent of each other. It's a very clean statement. In the xy, There is no cable extension, so it's a bit less clear what you call a vortex and what you don't call a vortex. In fact, Berezinskii-Kosterlitz-Thouless, I think in the initial work by Berezinskii, he already considers the villain model, which is quite, and maybe coupling. And there is another important paper, but I will maybe miss one name, which is by Rosset, Kadanov, Nelson, I think. Okay. And the fourth author. Okay, so I will go back to the slide just a little bit, and then we will start to see how one can prove this phase transition with on the mass side. Yes?
But if you take the VR model with the beta, you get exactly the same, so if you are small beta, so you have polynomial decay, do they think that you have the same critical exponent in the new xy?
Ah, the alpha of t?
Yeah, exactly.
No, it's not the same.
Okay, it's not the same.
No.
Okay.
But both models, they have a change of temperature.
But they don't have the same exponent.
No, yes.
Okay.
And they don't have the same critical point either.
Ah, okay.
No, but they look alike. I will define properly the villain model in a few minutes. But for those who've never seen it, I keep saying about the villain model, but I didn't even define it.
In the Bloom-Katz picture, that's supposed to be kind of that the phenomena that those pairs would attract to each other and then it would collapse completely at some point. Does the discrete model see this phenomena in some way?
Yes, so that's a very good question. So this whole physics explanation of the vortex binding, the closest proof of this phenomenon is in Fröhlich-Spencer, not in the later works. They even have a statement about this screening versus no screening of those charges. But as far as I know, there is no proof, geometric proof, that there is a binding of those plus and minus vortices.
Yeah.
So it's only through certain observables of the system that you detect something. But I have never seen a proof which says at low temperature you can find a combinatorial pairing between the plus and minuses which travel at distance less than through the vent, for example. While at high temperature there is no such possible pairing. So this would be a combinatorial justification of the binding, but as far as I know, this you cannot see it in their proof. I first claimed this to Tom, and he said no. And then I kept, eventually said, okay, maybe, but it was, I don't know if I convinced him, but I'm quite pleased. So, I still want to do one last slide before going for quite a while on the blackboard. So this was the one vortex anti-vortex binding, and at low temperature they're supposed to be close to each other. So here I should make maybe a remark. Those pictures, they're very beautiful. I like them very much. We've used those with Velio for more than 5 years now. But they're cheating a little bit. So it's a Markov chain on the XY model. And we stop the Markov chain before reaching equilibrium where the pictures are less nice. So vortices do exist in the XY model. They are responsible for the true BKT transition, which is now rigorously proven. But to see those, maybe beta has to be very large. So we do stop the Markov chain before it's... and if you play with the website, there must be something wrong in the Markov chain because there is a cycle. The colors go along a cycle, which for those systems, the measure is reversible. So there is something strange. But still, it produces nice pictures which convey the main idea.
So is there any result about mixing for XY, let's say in the regime where there's polynomial geometry? Because for Ising, like it's known that okay, so in the exponential decay phase is should be logarithmically fast mixing, right? Mm-hmm. And at the critical point it's polynomial, and then obviously in the bottleneck phase you will have exponential, whereas.
So if by mixing you would want to say that whatever you see here, this is polynomially uncorrelated with what you see here, that's not known. Would be nice, but it's not known. I'm happy to discuss. So that's one slide about the idea behind all the existing proofs of BKT. And the idea is quite nice and easy to explain at this stage. I stated for you what is the BKT transition. It singles out a different behavior, a power law behavior at low temperature versus this exponential behavior. If you were to prove this phase transition directly on the S1 valued spin system, it's not known. There is no direct proof that I've heard so far. And the reason is probably because of Mermin-Wagner. The system never has any symmetry breaking or anything. So the idea of the proof is to proceed by duality, to use the fact that the Fourier dual of S1 is Z. So you will rewrite the system via a Fourier transform. We will go to a dual model which is now Z valued. And now the beauty of this is that Z is a discrete space, and discrete valued spin system, they have a much higher chance to have a symmetry breaking. And that's exactly what will happen. This doesn't have symmetry breaking by Mermin-Wagner, but the dual model will have symmetry breaking. So we will see that the dual of those will be a Z-valued model, so a random interface on top of Z2 whose spins are in Z, not in R. And we will also see that the dual of the high temperature XY will be a low temperature Z-valued model. And in fact, this part of the phase diagram is easy. It's easy to show that if the temperature is very high in the XY model, you do have exponential decay. I didn't do it, but it's not difficult. And in the same fashion, its dual model is also easy to show that at low temperature for this model, you have something which breaks the symmetry. So unfortunately, easy is mapped to easy, so it's not there is no shortcut here. This is the same Peierls argument than the one I have shown during the break on Tuesday. So that's easy. What is difficult is that the low temperature XY is mapped to a high temperature Z-valued model. And what is difficult there is to prove that the Z-valued high temperature height model does not have symmetry breaking, that it's delocalized and that it doesn't remember what the Dirichlet boundary condition, for example, is at large distances. So proving that this delocalizes, if it was R-valued, it would be easy. It would be Mermin-Wagner, in fact. But the fact this is Z-valued prevents you from using those spin waves and shifting the system. And so proving delocalization is hard. And the first time it was done, it was by Fröhlich and Spencer in '81. And in some other settings that are not quite those, if you know about the dimer model, there is an associated 8 function. There it's not a duality like Fourier, it's a direct coupling between the two. But it has been proved, for example, by Kenyon, or that those discrete valued, Z-valued 8 function for the dimer model also delocalizes, so the dimer is a bit a high temperature phase. But there were few proofs, and a few years ago, Pete Lammers found a rather robust proof of delocalization for those Z-valued models, so it's a very nice work. And this is why, shortly after, there were 2 new ways of understanding BKT. And now, with all those works, with a further recent work by Pete Lammers, it's known that delocalization is equivalent to power law decay. And that kind of equivalence was not present in Fröhlich-Spencer work. So if you are localized, you are exponential decay. If you are delocalized, you are power law decay. So recently, the understanding is better. And what I want to do now on the blackboard is to explain to you what is this duality for a model which is a little bit easier than the XY, but I will still mention the XY, which is called the villain model. So I will go to the blackboard and I will define 3 models that live on the unit circle S1. One of them will be the XY. The second one will be the Wiener model, on which I will focus most on in the rest of the last lecture. And the last one, I will just mention it to emphasize one key point, will be a geodesic built S1 valued model. So let me put maybe 3 models, 3 S1 valued models. S1 valued model. The first one, I will try to put very little space on this one because I already insisted a lot about this one. This is the XY. And here, P lambda beta xy of theta is proportional to product over edges. I will write it like that here. Exponential beta cosine of theta I minus theta j. So if I want to write it well, it's d of this with respect to the uniform measure is proportional to this Radon-Nikodym derivative. So that's xy, and I already discussed a lot about this one. Maybe let me even gain more space by putting it down. And okay, maybe I will emphasize the S2 valued case at the same time. The classical Heisenberg in this case it would be P lambda beta Heisenberg of sigma, which is now S2 valued at each point, is proportional at product over I next to J of E beta sigma I scalar products in R3 with sigma J. So what is my second model? My second model is called the Wiener model. So it's still a model on the same state space on S1 to the power Z2 or ZD, but I will stick to D equals 2. And to define things well, I will define it on S1 to the power lambda, a subbox of Z2. And similarly as the XY model, it will share the same symmetry group, namely O2 or SO2. So I want to define another ferromagnetic type model, S1 valued, with same symmetry group, but which will be slightly easier to analyze for a reason which will come in a second. Maybe I can explain here why this model was natural. If you want to do the Fourier transform of the XY model, there is one periodic function which is singled out here, which is the function fxy of theta, which is defined as E of beta cosine theta. That's a 2-pi periodic function. And if you want to do the Fourier transform, you will naturally have to compute the Fourier coefficient of this. So this will be written as sum over k of fxy Fourier coefficient of this periodic function, e to the I k theta. And the problem is that the Fourier coefficient of this periodic function is not nasty for everyone. It's a case-modified Bessel function, but at least to me, this is slightly intimidating. So the whole idea of the Wiener model is to replace this ferromagnetic interaction with an interaction which has the same flavor, but whose Fourier coefficients are much nicer for us. That's exactly what the Villain model will do. So the definition goes as follows. The weight of a collection of angles in the sense of the Radon-Nikodym, but I think I already insisted enough in the course on Tuesday that this is a dp Villain divided by d uniform measure on the 0 to pi angle. We want to replace this by still a nearest neighbor interaction, so I will still take a product over the edges in my graph lambda, but I will change the way theta I interacts with theta j. And here, I will write it like that. I will do two expressions. I will use the heat kernel on the unit circle between theta I and theta j. And I need a temperature. So to make it more and more pointing in the same direction, I will apply the heat kernel in an inverse way of the inverse temperature beta. So if beta is very, very large, and I have my unit circle here, if theta I is here, so this is e to the I theta I, if beta is huge, the heat kernel on the unit circle will look a little bit like a Gaussian, almost a Dirac point around theta I. So the Gibbs measure will want theta j to be very next to theta I, a little bit like in the XY model. So to be consistent with the previous model, I need my heat kernel to propagate just a little bit at very low temperature, while at very high temperature, the heat kernel will be basically uniform on the circle, and this is a very disordered spin system. The good thing with this is that it readily extends to S2 valued or Sn-1 valued. Let me try to do it in this box. So the Villain, let me do it on S2, would be P, I don't think it has a proper name, but classical, let's call it classical Villain Heisenberg. Maybe it's a terrible name. It's a Gibbs measure on S2 valued spins. So now I have sigma, and this will be proportional to product over I and j of the heat kernel on the S2 sphere along the time t equals 1 over beta of sigma I and sigma j. And this also has the property that if sigma I is here, the heat kernel at low temperature will be very concentrated next to it. In S1, you may also try to do something in S2, but this is a bit more nasty. But in S1, there is one advantage that this can be written down very easily. So let me do it here, maybe with a different color. And I should finish very quickly. I don't have a nice second color. Let me do it in white. So let me explicitly write what is the heat kernel of this. So that's easy to do if you start from the unit circle here, and this is theta I. How can you do the heat kernel which goes back to the circle? You just do the heat kernel of the Brownian motion, and you claim that theta j is the same as theta j plus 2 pi, theta j minus 2 pi, and so on. So your heat kernel of the circle is the sum of all those heat kernels along the R. And that means that the heat kernel here is very simply written like that. It's a sum over integers in Z of exponential minus beta over 2 theta I minus theta j plus 2 pi times m squared. And maybe I miss 1 over squared beta or something, but I don't care. This, as usual in Gibbs measure, will not affect the system. So the villain model is this. And the nice feature of this is that I can, exactly as in the xy, I can just remember what is the interaction. Let me call it F villain of theta, which will be now sum over m of exponential minus beta over 2, theta plus 2 pi m squared. So it's a slightly less nice function of theta, a priori, but it has a very nice property that the Fourier coefficient of this periodic function of theta as a function of the Fourier mode k. It's an easy exercise to show that those are Gaussians. So this is exactly exponential minus 1 over 2 beta times k squared. And that's the place where we see that there is an inversion of temperature. The beta, which is here, goes to the denominator, so it's a bit this uncertainty principle, a very easy instance of that. But in the second lecture today, we will work with this Fourier transform, and this little computation on this part of the blackboard explains why the z-valued model pops out. Okay, I wanted to do the model 3, but I think I would be way too delayed.